Hi, in this video we will look at the common uses and properties of aluminium metal and explore in detail how aluminium is extracted from its ore bauxite. Now, to get the most from this video, you should have a good understanding of how electrolysis works. Aluminium is a shiny silvery coloured metal with many desirable properties, including a low density, where it is commonly used in the aviation and car industries to make parts and body panels. Aluminium is also an excellent electrical and thermal conductor. Now, this property is taken advantage of when aluminium is used to make power cables and pots and pans and other cooking utensils at home. Aluminium is also an attractive metal and it is used to make items such as mobile phone cases. Its attractive appearance and corrosion-resistant properties make aluminium ideal for the use in cladding in many office buildings and in the construction industry. But perhaps the best known uses for aluminium is its use in the kitchen as kitchen foil or cooking foil and in making cans for fizzy drinks. The method used to extract a metal from its ore depends mainly on the position of the metal in the reactivity series. For metals below carbon in the reactivity series, the most common method used to extract a metal from its ore is simply by heating with carbon or charcoal in a metal crucible. This is shown in the diagram on screen. Here, the metal ore is simply mixed with carbon or charcoal in the crucible and heated strongly. The carbon present will reduce the metal oxide in the metal ore and produce the metal. This method is particularly good for extracting metals such as iron and lead from their ores. A simple word equation to show this reduction reaction is also shown on screen. While metals below carbon in the reactivity series can be easily extracted from their ores by heating with carbon or charcoal, metals above carbon in the reactivity series cannot be extracted this way. Instead, these metals are extracted from their ores using a method called electrolysis. Heating with carbon or charcoal simply does not supply enough energy to extract these reactive metals from their metal ores. Now, electrolysis simply involves passing an electrical current through a melted or molten ionic compound. This process requires lots of energy, both to melt the ionic compound found in the metal ore and to split up the ionic compound back into the elements that make it up. The main ore of aluminium is called bauxite, and bauxite ore may contain up to 60% aluminium compounds, with the main impurities being sand, clay and iron compounds such as iron oxide. Now, before any electrolysis is carried out to extract aluminium present in the bauxite, it is first purified to form a white powder called alumina. Now, alumina is simply aluminium oxide. Aluminium oxide has the formula Al2O3 and it contains aluminium ions with the 3+ charge and oxide ions with the 2- charge. Now, aluminium oxide is an ionic compound with a giant lattice structure, and the ionic bonds present between the aluminium ions and the oxide ions are very strong. Consequently, alumina or aluminium oxide has a very high melting point, well above 2000 degrees Celsius. Now, to split up aluminium oxide into the elements aluminium and oxygen using electrolysis, this giant ionic lattice structure needs to be broken down so that the aluminium ions and oxide ions are free to move. This can be achieved in two ways, either by melting the aluminium oxide to form a liquid or by dissolving it in a suitable solvent. Both of these methods will result in the giant ionic lattice structure breaking up to form ions which are free to move. Now, with such a high melting point, melting aluminium oxide will prove a challenge, and it would also be very expensive. Luckily, it was discovered that a rare mineral called cryolite, which itself melts around 1000 degrees Celsius, would dissolve the aluminium oxide, and the solution formed will conduct electricity. This means that when the aluminium oxide dissolves in cryolite, the ionic lattice breaks down, and the aluminium ions and oxide ions are free to move to form an electrolyte or a solution that will conduct electricity. The diagram on screen shows an outline of a typical cell used to extract aluminium metal from alumina or aluminium oxide. The electrolytic cell consists of a steel shell which is lined with a refractory or heat-resistant material and a thick layer of graphite which forms the cathode. The anodes consists of large blocks of graphite which are dipped into the molten electrolyte. Now the electrolyte consists of a mixture of molten cryolite and dissolved aluminium oxide at a temperature of about 950 degrees Celsius. Fresh alumina and cryolite are added to the top of the cell regularly using large hoppers, which are not shown in the diagram. Now aluminium metal, which forms at the cathode, has a melting point of 660 degrees Celsius, and since the cell operates above this temperature, the aluminium which is formed will be in a liquid state, and so it will be easy to remove from the cell. Now recall that the cathode is the negatively charged terminal in an electrolytic cell. Now as the electrolysis reaction takes place, the positively charged aluminium ions will be attracted to the negatively charged cathode. Here they will pick up 3 electrons and form aluminium atoms. An ion-electron half equation for this reduction reaction is shown. The image shown on screen shows the positively charged anodes. During the electrolysis of the aluminium oxide, the negatively charged oxide ions present in the electrolyte will be attracted to the positively charged anodes, where they will be oxidized to form oxygen atoms. That is, each oxide ion will lose 2 electrons on the surface of the anodes to form oxygen atoms. Now since each oxide ion has a 2- charge, it will lose 2 electrons when it forms an oxygen atom. An ion-electron half equation for this oxidation reaction is shown. However, recall that oxygen gas is a diatomic gas. That is, it consists of small molecules made up of 2 oxygen atoms. Now a molecule of oxygen will form when 2 atoms of oxygen join together after they leave the anode. This is shown in the animation on screen. This means that the ion-electron half equation will need to be multiplied by a factor of 2 to account for the formation of the new oxygen molecule. You might therefore reasonably expect that oxygen gas will be produced at the anode. But recall that the anodes are made of carbon or graphite, and they are at a high temperature of around 950 degrees Celsius. So the carbon anodes will simply react with the oxygen gas produced here to form carbon dioxide gas. This means that the anodes are slowly burning away and will need to be regularly replaced. The 2 diagrams on screen outline the oxidation and reduction reactions taking place at the anode and the cathode during the electrolysis of aluminium oxide. The 2 half equations for the reactions taking place at the anode and cathode are also shown. However, you may notice that in terms of electrons, these 2 equations are not balanced. The oxidation reaction at the anode involves the loss of 4 electrons from 2 oxide ions, while the reduction reaction at the cathode involves the aluminium ions gaining 3 electrons. Now to balance these 2 half equations, simply multiply the anode half equation by 3 and the cathode half equation by 4. This will result in 12 electrons being present in both half equations. Now to get the overall equation for this redox reaction, simply combine the 2 half equations. The 12 electrons being present in both sides of the equations will simply cancel each other out. Hi, thanks for watching. If you found this video helpful or would simply like more information, then why not visit the website that accompanies these videos? The links are in the description below. If you enjoyed the video, then please consider liking and subscribing. Thank you.